Suppose we have now that y equals sine u, where u is some differentiable function of x. And we now want to find dy dx. Well, you see, the point is that we know that the derivative of sine u with respect to u would be cosine u. What we want is the derivative of sine u with respect to x. And we motivate the chain rule the same way as we did before. It happens to be that we're dealing with the specific value called sine, but it could have been any old function. How would you differentiate f of u with respect to x if you knew how to differentiate f of u with respect to u? And the answer is you would just differentiate with respect to u and multiply that by a derivative of u with respect to x. In other words, we get the result what? That since dy du is cosine u, we get that the derivative of sine u with respect to x is cosine u times du dx. And by the way, one rather nice application of this is that it gives us a very quick way of getting the derivative of cosine x. After all, our basic identity is that cosine x is sine pi over 2 minus x. Again, a number or an angle. Either way, as long as the measurement is in radians, it makes no difference whether you think of this as being an angle or being a number, the answer will be the same. The idea is this. To take the derivative of cosine x with respect to x, all I have to differentiate is sine pi over 2 minus x with respect to x. But I know how to do that. Namely, the derivative of sine pi over 2 minus x is cosine pi over 2 minus x, and by the chain rule, times the derivative of this with respect to x. Well, pi over 2 is a constant. The derivative of minus x is minus 1. And then remembering that the cosine of pi over 2 minus x is sine x, I now have the result that the derivative of the cosine is minus the sine. And again, I can do all sorts of things this way. If I want the derivative of the tangent, I can write tangent as sine over cosine, use the quotient rule. You see, as soon as I make one breakthrough, all of the previous body of calculus comes to my rescue, so to speak. By the way, what I'd like to do now is point out why, from a physical point of view, we like circular functions to be independent of angles and the like. With the results that we've derived so far, it's rather easy to derive one more result. Namely, let's assume that a particle is moving along the x-axis. I'm going to start with the answer, sort of, and work backwards. According to the rule, x equals sine kt, where t is time, and k is a constant. Then its speed, dx dt, is what? Is the derivative of sine kt, which is cosine kt, times the derivative of what's inside with respect to t. In other words, it's k cosine kt. The second derivative of x with respect to t, namely the acceleration, is what? How do you differentiate the cosine? The derivative of the cosine is minus the sine. By the chain rule, I must multiply by the derivative of kt with respect to t, which gives me another factor of t over here. Remembering that x equals sine kt, I arrive at this particular so-called differential equation. And what does this say? It says that d2x dt squared, the acceleration, is proportional to the displacement, the distance traveled, but in the opposite direction. You see, k squared can't be negative, so minus k squared can't be positive. This says what? The acceleration is proportional to the displacement, but in the opposite direction. Does that problem require any knowledge of angles to solve? Notice that this is a perfectly good physical problem. It's known as simple harmonic motion. And all I'm trying to have you see is that by inventing the circular functions in the proper way, not only can we do their calculus, but even more importantly, if we reverse these steps, for example, we can show that to solve the physical problem of simple harmonic motion, we have to know the so-called circular trigonometric functions. And this is a far cry, you see, from using trigonometry in the sense that the surveyor uses trigonometry. You see, this ties up with my initial hang-up that I was telling you about at the beginning of the program. By the way, in closing, I should also make reference to something that we pointed out in our last lecture, namely inverse differentiation. Keep in mind also that as you read the calculus of the trigonometric functions, that the fact that we know that the derivative of sine u with respect to u is cosine u gives us, with a switch in emphasis, the result that the integral cosine u du is sine u plus a constant. And in a similar way, since the derivative of cosine is minus the sine, the integral of sine u with respect to u is minus cosine u plus a constant. Be careful. Notice how the signs can screw you up. Namely, they're in the opposite sense when you're integrating as when you were differentiating. But again, these are the details which I expect you can have come out in the wash rather nicely.